Okay, tonight we have to talk about 5.4, exponential and log equations. Now you've already done a lot of these. You've done things like using the one-to-one property. If you had 2 to the x is equal to 32, that's an exponential equation, which we'll solve. 2 to the x is 2 to the 5, so simply x equals 5. You've also done things like using our if and only if property. Yes, Nathan, it is not a simple if, it's an if and only if. So if I start with an equation that's like a log equation, base 3 of x is equal to 2, I'm going to rewrite this as an exponential using my if and only if. And then it becomes base 3 raised to the exponent 2, because the answer to the log is always the exponent, and that leaves me with equals x. And so I can solve this easily, x equals 9. Right, you can also go both ways. If you start with a log, write it as an exponential. If you start with an exponential, I can use my if and only if statement to write it as a log equation. So these equivalent forms are going to be helping me solve these. So this is true if I can write it as a log form, the log with base e, the answer to the log will be the exponent x, and that leaves the 7 here. So x is log base e of 7, but of course log base e is an ln. So we'll write that as x is equal to ln 7. Alright, let's give you some for you to try. The first one you should try, ln x minus ln 3 is equal to 0. Give it a try, give it a pause, use all your strategies. Okay, I get an answer x equals 3. I decided to use the one-to-one property. I could add the log 3 to the other side and use one-to-one. Try the next one, log x is a -1, and pause it. Okay, I hope I didn't confuse you too much with this one. You're using the if and only if statement. Remember, with no base written, the base is assumed to be a 10 for the common log. So there's my base 10 raised to the exponent -1. Alright. Alright, sometimes it's important to make sure you isolate either the logarithm or the exponential before you apply some of these strategies. So in this case, I've got a lot of things going on the same side as the exponential. So I'm going to add 4 to both sides. And then I'm going to divide by 2. Forgive me for using a decimal. I'm going to, now that I have isolated that exponential, use my if and only if statement to say log with a base 3, because that's the base of this exponential. The answer to the logarithm is the exponent. Okay, so that's the beauty here, is what used to be a variable in an exponent is now a variable that's not in a pi in an exponent somewhere, which is so difficult to work with. So that's what logs do for us. And I have to put a 7.5 here to finish out my if and only if statement. So now I've really taken care of everything. I just need to finish the little algebra to solve for t. So t is 5 plus log base 3 of 7.5. But there's one more thing. I still can't get an answer. Oops, I still have to divide by 2. But then I have to worry about this log base 3. So let me call this 5 halves plus 1/2 log base 3 of 7.5. I can't put this in my calculator yet and actually find a number. I've got a log button, which is base 10, and I've got an ln button, which is of course the base e, the natural base. Where's the button for log base 3? Well, that of course is where the change of base formula comes in. So I'm going to use that to write my answer up here. 5 halves plus 1/2. I'm going to say log of 7.5 over log of 3. And that's my answer for t. If I go ahead and put that in my calculator, then you should try this to make sure you can get your your button strokes correct, get your parentheses in all the right places, you're going to get approximately, because it's going to be rounded, 3.417. Okay, try this one. What if you had log base 5 of x is equal to 4? Let's see if you can solve that. Okay, that problem's not too bad. Just use your if and only if statement, 5 to the 4th is equal to x. And we could actually find a number there. Okay, this next question, you know, remember we're always trying to isolate that logarithm. And this one's tricky. You might think one-to-one property because I got log on the left, log on the right. But that doesn't work because you've got this minus sign right there. You've got 2 logs on the left. So we need another strategy that's going to allow us to condense those 2 logarithms into 1 logarithm. And of course, that's exactly what we did the day before. On properties of logarithms, we can condense those 2 using that quotient property. So these 2 on the left will condense log base 6. Because it's a minus sign, I'm going to divide the first argument over the second argument. Now I've got the log on the left, log on the right with the bases agreeing. So it's a one-to-one property. 3x plus 14 over 5 is 2x, and I can simply solve for x here. 3x plus 14 is 10x. And let's see, 14 is 7x, therefore x equals 2. And we got it. Alright, you try this one. It's a log of 5x plus a log of x minus 1 is equal to 2. Try that and pause it. I'll be right back. Okay, so there's how I did it. I used the product property to go ahead and condense the logarithms on the left. And then I used my if and only if statement. And then it was a matter of solving for x. And so I have found 2 solutions for x. But here's the kicker. One's extraneous. And what happened was the negative 4 does not belong in the domain of either logarithms. Okay? So remember, when you had a log, the graph looked like this. Right? And so you had this little asymptote here. And so over here, left of that y-axis is undefined. So the domain of this logarithm is x has to be greater than 0. Okay? So that would be true for this logarithm, that 5x had to be greater than 0, which is the same as saying x is greater than 0. But here, this one does have a shift, so x minus 1 has to be greater than 0 for this second logarithm, or x has to be greater than 1 is the domain for this second logarithm. Well, I just wanted to show you what both those domains would be, but in either case, x equal minus 4 is a bad solution, and you're left with x equal 1. So be sure that you're always checking your domains when you give a final answer. Okay, here's a word problem for us. The question is, if you deposit $500 in a bank account at 6.75% interest rate, it is compounded continuously, how long will it take to double your money? I know we talked about doubling money, or doubling the penny, but that was every day. This is a compound continuous, so that takes precedent here. And the formula is A is equal to P e to the RT. Okay, so I'm going to use this. To double my money, I'm starting with $500. That's the P. I want to double that, so that's the account amount, $1,000. I have my E, the natural base, the R, 0.0675 T. Okay, so there we have. Remembered to move the decimal on my percentage, and I have T, the variable, in the exponent. So I'm going to do just like we've been doing. I'm going to isolate that exponential, divide both sides by 500. And there's my 2 for doubling. 2 is equal to e to the 0.0675 t if and only if log base e of log base e of 2 is equal to 0.0675 t. The answer to the log here was the exponent here. So now I just have to solve this. I'm going to, let me go to the next page. Of course, this is ln2 is equal to 0.0675 t. I just need to divide both sides by the 0.0765. So ln of 2 divided by 0.0675 is equal to t. Put that in my calculator. T is approximately 10.27 years. Don't forget your unit.